Hi everybody. Sorry for the late announcement, but we're going to have this lecture be online. This is for Wednesday, the 11th of March, class number 25. Let's take a look at some announcements here. Homework number 8 is still due before class on Friday the 13th. That's the assignment that's related to steady uniform flow, which is mostly Manning's equation. And then the first part of non-uniform flow, where you're having to look at the specific energy, total energy, those sorts of ideas. And so that assignment is due as originally announced on Friday the 13th before class. And then also as a reminder, I've been working through the demand estimation that you've done, and phase 2 of your project is going to be due on Friday, March 20th. And so that's where you're doing your first attempt at sizing the network. And as I illustrated in our previous class meeting, you're going to need to provide 2 PDF maps of your network. A network that shows your system at full flow rate, which is where it's going to be the lower pressures, and then your system where there's no flow demands, and that's going to be the static condition where the pressures are high. So I want to see your network and how it performs at those two extremes. I'm going to show you in just a moment one of the student submissions for the demand estimation, someone who I think did a really nice job and who I'd like you to kind of emulate for your final submission. Of course, if you didn't do as well as you'd like on the draft, you always have the final report in the end to make corrections to your initial estimates and then submit the improved version, which is still worth half of the grade, towards the end of the course. So I'll show you that in a moment. Today's lecture is focusing on some of the ideas that we initially started in our previous class on Monday, and so this lecture is covering total energy, specific energy, and some ideas having to do with critical flow. So that's the flow regime and using the Froude number and depth relative to critical depth to understand the flow conditions that we could expect to see. Okay, let's take a moment to go through the demand estimation for one of your classmates. I wanted to point out the 3 things that I really liked about this student's draft submission for demand estimation. The first thing is that there was a really cohesive, easy to follow narrative that explained the thinking and the assumptions that were behind the calculations. So it's not just the summary of the flow rates and it's not just the calculations themselves, but this is kind of a description of what data was obtained and what assumptions went into generating the flow rates. And so you can see this student has a couple of pages devoted to describing what's going on at each of the locations, what's the data source, how the flow rates were generated. So this helps me a lot when I'm going through the calculations themselves. If there's some of the calculations that I don't notice, then I can go back up here into the narrative and understand a little bit further. You'll notice that there's also some of the data sources inside the calculations. Sometimes those data sources are referred to specifically. Maybe it would have been better if they'd been numbered, and then the number, like where the data source was used, would be indicated more explicitly. But overall, this student did such a nice job, I don't even want to emphasize too much the concerns that I have. All right, so here's the summary table, and this is everyone had to fill out some sort of a summary table for their flow rates. And then the calculations, hand calculations are totally fine. In fact, I prefer it. I think it's easier for me to follow hand calculations than if you're doing the calculations with a spreadsheet, and certainly easier to follow and better looking in the end than calculations that are done like using Microsoft Word. So what I liked about this is it shows all of the steps. The handwriting is clear enough, the units are included, and I can see the summary flow rate. So this is what I hope to see from everyone. If you haven't gone into that much detail in your draft submission, you can make improvements and correction for the final report that you have to submit in the end. And so you can just see that everything's easy to see how you got from, for instance, with the golf course, how you got from a certain precipitation amount, and in the end, how that was converted into liters per second. Connecting the dots. I really want to understand what you were assuming in these calculations, and so the clarity and the linearity of your solution is really important. So I appreciate the great job that this student did.
All right. Alternate depths are situations where the same amount of specific energy yields 2 different depths of flow. And so if you draw a vertical line from any particular specific energy and you cross the graph in two locations, then that means that there's two different flow depths that could occur. And so if the depth is 0.5 meters, you can solve for the specific energy that goes along with that depth just by, from the graph, going over, intersecting. The other way to find the specific energy is just to substitute in the depth of 0.5 here, and then finding out what would be the cross-sectional area for this width of 4 and the depth of 0.5. So you put in the cross-sectional area, and so you're finding both the velocity head and the depth term for specific energy. And to solve for the alternate depth, what we would do here is we would find out the total specific energy at one of the depths, and then we'll find the amount of specific energy being the same for the other depth. Does anybody have a marker? There isn't one here in the classroom, but I can usually count on at least one of you guys to have it. Thank you very much. All right, so let me do this one on the whiteboard. Thank you. If we have a depth of, so y is 0.5 meters, then we know specific energy E is the depth plus q squared divided by 2ga squared. And we're going to consider this case of q is 10 cubic meters per second. And so what that means is that the specific energy is 0.5 meters, and that first part is just the depth term, and then 10 cubic meters per second squared divided by 2g, which is 9.81, and then the cross-sectional area. And the cross-sectional area is going to be whatever the depth is times 4 meters. And so if we're doing this for a depth of 0.5, then area is 0.5 times the width of 4, so the area is 2. Okay, so the area is 2, and we're squaring it from the formula. So the total specific energy is 1.774 meters. So that's how much specific energy there is when the depth is 0.5 meters. So let's look over here. 0.5 corresponds to 1.774. Now to find the alternate depth, what we're trying to find out is what is this other crossover point of the same curve. And what we can do is we can say that 1.774 meters is y plus 100 divided by 2 times 9.81 times 4y squared. So we're putting that in terms of the unknown depth, this other unknown depth that can give you the same amount of energy. Okay, so y is the unknown depth. We still know that the flow rate is 10, so 10 squared divided by 2g, and then the cross-sectional area is going to be 4 times whatever the depth is, squared. So we can rearrange this. This is going to be a cubic equation. So we're going to multiply each term by y squared. And so that's 1.774 y squared is equal to y cubed plus 0.3186 divided by, this whole term. This last one is the same thing as 0.3186 divided by y squared. So if we just have the 100 divided by 2 times 9.81 times 4 squared. So So that cubic equation then is plus 0.3186. So there's going to be multiple roots to solve this equation. If we just rearrange it, it's y cubed minus 1.774 y squared plus 0.3186 is equal to 0. And if you put it into your calculator, what you'll find is that the three roots of this, one of them is negative 0.3842. Another one of the roots is the depth that we already knew, 0.50 meters. But then another one of the roots is the depth that we're looking for, 1.658 meters. And so that is the alternate depth, 1.658 meters. You could solve it numerically using the spreadsheet, but you can also solve it by finding the roots of that cubic equation. Any questions about alternate depths? One thing that we didn't account for was any sort of energy losses as the water goes from a transition from a supercritical to a subcritical depth. And in a hydraulic jump, like in reality, when the water goes from a supercritical depth to a subcritical depth, there is a lot of turbulence and quite a bit of energy is lost. We will account for and demonstrate those energy losses in the future. But just looking at the theory behind specific energy and alternate depths, we haven't yet accounted for any of those losses. Critical conditions, remember, correspond to the minimum amount of energy to convey a certain flow rate through a channel. And so it's where you have minimum specific energy. That means that if you look at this curve, there isn't any slope when you're at the minimum point. It's the vertical, completely vertical conditions. It's not sloped sideways like in the subcritical zone or in the supercritical zone. So this is the definition of specific energy. It's just the energy relative to the channel bottom at a given location. And if we take the derivative of that with respect to y on both sides, then this is where the Froude number equation comes from, where we're saying that the Froude number is equal to 1 at critical conditions. So the flow rate squared times the top width divided by g times a to the third power is equal to 1 at critical conditions. So if we rearrange that, so this was 1 on the right side, and we rearrange that so that now under critical conditions, if we want to find the critical depth, then regardless of the cross-sectional shape, it can be for a trapezoidal geometry or a half circle or a triangular geometry, this can always be used to tell you what's the critical depth. So just as an example, if you want to find the critical depth for a rectangular channel where the flow rate is 10 cubic meters per second and the channel width is going to be 4. This is that same rectangular channel that we've been talking about today. We can find the critical depth using this formula. Just by substituting in, okay, so it's q squared divided by g is equal to, now the cross-sectional area, if the width of the channel is 4 and the unknown depth is y sub c, so on the right-hand side of the equation, it would be 4 times yc cubed, and then it's going to be divided by b sub c. So b sub c is the channel width at the critical conditions, and the channel width is 4. So just substitute the 4 in there, and what that leads us to is that the y sub c is b sub c q squared divided by g to the 1/3 power, and then we multiply that by 1/4. So the critical depth is going to be 4 meters times 100, because the Q was 10, divided by 9.81 to the 1/3 power, and then times 1/4, so 0.86 meters. That is the full-blown equation for it, but here is a simplified way to find the critical depth only if you have a rectangular channel. So if you have a rectangular channel, meaning that the top width and the bottom width are the same, then what you can do is you can calculate something known as the flow per unit width. That's what the lowercase q means, is it means the overall flow rate Q divided by the channel width. And this formula can be used to find the critical depth only in a rectangular channel cross-section. So with the example that we've just been looking at, where the flow rate was the uppercase Q is 10 cubic meters per second, and the channel width B is 4 meters, then lowercase q is Q divided by B. So what we're saying is there's 10 cubic meters per second divided up among 4 meters of width. So the flow per unit width is 2.5 cubic meters per second per meter of width. And then the critical depth y sub c, we can only use this when conditions are it's rectangular channel. So it's going to be the flow per unit width, 2.5 meters squared per second, and square that divided by 9.81 meters per second squared, and then take the 1/3 power of that. So 2.5 squared divided by 9.81 and the 1/3 power, it again gives you the depth of 0.860 meters. So you can find the critical depth either according to like the full-blown formula that'll work for any kind of a shape, but a lot of time these problems that you're going to solve assumes a rectangular geometry, and so then if it's rectangular geometry you can use the simplified approach where it's based on the flow per unit width. All right. One last thing I wanted to tell you about is that you can sometimes face problems where they're asking you to determine the critical slope. And the critical slope is just how steep does it need to be to cause critical flow depth. And so this would be a combination of both the formula for critical geometry and also Manning's equation. So in this case, they would tell you what is the flow rate, the side slopes, the bottom width, and so you can use all those geometric parameters to set up Manning's equation. What you're trying to solve for is the slope that's going to give you the depth that corresponds to critical conditions. And so you'd start off, it's a two-step thing. First of all, we'd have to use the full version of the critical equation. We couldn't use this rectangular simplification that we just found. So you solve for the critical depth with this formula, and then you put that critical depth into Manning's equation, and I'll just briefly show you what the solution looks like for this one where you're finding the critical slope. So we know the area formula from that factor table. We've got the wetted perimeter, the W term, and everything. So with the critical depth equation, you can find this is the depth that corresponds to critical, this is the depth that's critical, and then you rearrange Manning's equation for the slope, and so you'll solve for that special how steep the channel has to be in order to cause the critical depth.